proof which I didn't quite succeed last time.
I checked on it is a group.
Yeah, anyway, but, now I also do it again. I mean, it's I just it is a simple thing, but I somehow got confused. So the proposition so I have G finite solvable group. And there's a chain. G equal 3, 0, 1, each n of subgroups such that hi plus 1 for all I is a normal subgroup. In each I, and the quotient is cyclic. Actually, so let's, I mean, it's in some sense quite simple. We take a chain in abelian groups and then we kind of, so that the quotient is abelian, then we squeeze in more subgroups in between the two successive groups here, so that the quotient is abelian, so that the quotient becomes cyclic. And this is, so let's see. So let G GL equal 1, here a chain of subgroups which makes it into a solvable group, so such that Gi plus 1 is normal Gi and Gi plus 1 is abelian. And to save some space, whenever such a chain I call a normal chain for G. Okay. I don't know whether. Okay. Now I fix some I, so I have this chain I number from one of these indices. So it's enough to show that between Gi and Gi plus 1 I can put some subgroups so that the successive quotients are cyclic. So it is enough to find a chain. So for each I have to do this, but for any given I, to find a chain Gi is equal to H0 contains H1 and so on, H say M, which is Gi plus 1, such that for J, Hj modulo Hj plus 1. So this is of subgroups, obviously. So subgroups such that Hj modulo Hj plus 1 is cyclic for all J. Obviously these, now as the quotient Gi modulo Gi plus 1 is an abelian group. So if I have if I look at the natural projection, so P from Gi from Gi modulo Gi plus 1, the natural projection. And we have that such an, if I have such a subgroup Hj, this is equal to P to the minus 1 of P of Hj. And P of Hj is a subgroup of this abelian group, and so therefore it's a normal subgroup. Now, Hj is automatically a normal subgroup of Gi. So P of Hj is a normal subgroup of Gi modulo Gi plus 1. And thus it follows that Hj, which is the inverse image under homomorphism, is a normal subgroup of Gi, and therefore also okay, anyway. So now so we want to find such a thing. So we use induction on the index of Gi plus 1 in Gi. So if say R is equal to 1, so Gi is equal to Gi plus 1, whatever thing is trivial. In some sense we could also exclude that. Anyway, let now A be an element in Gi divided by Gi plus 1, which is not the unit element of this thing, then A is a cyclic subgroup of Gi modulo Gi plus 1, and we put N to be the inverse image of this cyclic subgroup, which is a subgroup of Gi. So this is again, for the same reason as before, is a normal subgroup of Gi. Because it's the inverse image of the normal subgroup of this Gi modulo I plus 1, because all subgroups of the Gi modulo I plus 1 are normal subgroups. And if I look at the index of this thing and this is certainly smaller than R, because and this is this group is strictly bigger than Gi plus 1. So thus, by induction, there is a normal change. So what is it? Gi contains H0, contains and so on, contains some Hn minus 1, which is n, with cyclic quotients. So I mean, H J modulo Hj plus 1 is cyclic. So we just now add a Gi plus 1 at the end, and we have the chain we want. So thus Hgi is 0, Hm minus 1, which is n, means Hm, which is defined to be Gi, is also a chain of normal, is a normal chain again. We had before all successive quotients Hj modulo Hj plus 1 are cyclic, and here, so we only have to see that the last one is cyclic, but the last one is what we have here, and Hm minus 1 divided by Hm is equal to A is cyclic. Okay, so it's very, it's a simple thing. You can just one by one just take one element and take the subgroup generated by it, and then you take this as a step, and then you do the same with what remains. So this is a simple exercise which I failed to do correctly on the first attempt, but now we want to apply it to the question. So the claim was that everything clear?
Why is this Hj equals to p minus 1 of pi of Hj?
Well, it's a Hj is a subgroup of Gi, which contains Gi plus 1. So then if you divide by it and come back, you get it back. I mean, there's no, just because it already contains it. So we have this theorem that we finally want to prove. So K field of characteristic 0, F in Kx polynomial with kernel of F solvable. Then it follows that is solvable for radicals. By the way, I mean, you could ask yourself, for instance, how one finds Cardano's formula. You can also find it this way, because now we prove this. No? If one applies this proof in the case of degree 3 polynomials, it will somehow, if one looks carefully at what one does, give us Cardano's formula. Obviously with some work, because so we had already started, but I think I have to set up annotation again. So we take L, the splitting field of F over K, so that the chiral group of L over K is the chiral group of F, and so and I put N to be the number of elements in this chiral group. So we have a chain. So as the chiral group of S is solvable, we have a chain so now I start with the other way around, but anyway, so 1 is contained in Gm, contained in Gi, contained in Gi plus 1, contained and so on until we finally get G0, which is the chiral group of L over K. So it's a normal chain again. So these are subgroups such that the successive quotients are so that each one is normal each one is normal in the previous one with cyclic quotients. By the proposition we just proved. So the thing is solvable. So if it's solvable, we can have such a normal chain where the quotients are cyclic and not just to be.
I have a question
Yeah.
about the theorem. Is the converse true?
Which one?
The last theorem. If F is always solvable by article, does that mean that the Galois group is solvable?
Yeah, no, that we proved. No, I mean this was the claim was that so the theorem of Galois was that the polynomial is solvable by radicals if and only if the Galois group is solvable. And so we proved one direction already, and now I prove the other direction. I don't know. Okay, so we have this, and so now we can look at the corresponding fixed fields, and we get a chain of fields. So, what?
Sorry. If the Galois group of F over the field K is solvable,
Yeah.
can we say then that the Galois group of F over the algebraic closure of F is still solvable? Or an extension generally?
Well, so yeah, I mean, not about algebraic closure. That the algebraic closure. I mean, it would also be solved, but the Galois group would be somehow trivial or something. But now, so if you have an extension, I think. So what you would have that the Galois group is a quotient, and you know that the quotient of if you have a surjective homomorphism from a group to another group, then you get that the image is also solvable, and so then it follows. It's also clear that it has to be.
Yeah, so we can just prove that the degree 5 is not solvable by radical. Because if we can prove it for a degree, then for any polynomial of degree higher, we cannot do it. Is that correct?
Well, no, it depends on the polynomial whether it's solvable or not.
Because if I have a polynomial of degree higher than 5,
Yeah.
I can, in some extension of R, I can do a decomposition of polynomial of degree 5 with something of degree less than 5, of power 5. I mean, some product of polynomials of degree 5 and the last one is less than 5.
Well, maybe.
Then since I cannot express each one by radical, then I can.
Well, I'm not quite sure whether this works. We would have to see whether it's really, power. I mean, it's easy to say that, but actually, I'm not entirely sure whether one actually can do that. And here you kind of get a direct state, like that. And it's anyway, this would be just for the general statement that not every polynomial is. But obviously there are irreducible polynomials of arbitrary degree which are solvable. It depends on what the Galois group is. So, okay, let me just, so we put for each I, put Li to be the fixed field of Gi in L. So we get the corresponding chain of fields. So then we have a chain of fields. I can look at which is L is equal to Lm and m minus 1 L0, which is equal to K. So we use the fundamental theorem of Galois theory. And so this is a chain of intermediate fields. And furthermore, we know we have that Li over Li minus 1 is the Gottshe extension for all I. This is because each one is a normal subgroup in the next, and so that means that the corresponding extension is a Gottshe extension. That was also part of the fundamental of Gottshe. And we have obviously that the Gottsche root of Li over Li minus 1 is precisely equal to the corresponding quotient Gi minus 1 over Gi. No, this was also part of the fundamental theorem, of the second part of the fundamental theorem of Gottsche theorem, that is cyclic, because that we had assumed. And its order dividing this number n, because the n is the number of elements of the Gottsche group, which is our G, and so we have every subgroup has an order which divides n, and if we take two numbers which divide n and divide them by each other, we get something which divides n. Okay, so we take theta, a primitive entity of unity, and we add psi, this theta, to all these fields to get another extension. So we have L theta over, which is an m of theta and so on until L0 theta k theta is over k is a chain of is a chain of fields, and we want to show that this chain here establishes L of theta over k as a radical extension. This chain shows that L of theta over k is a radical extension. So by which as you know, radical extension means you have a chain of fields, so that each step is obtained by adding one element such that a certain nth power of it lies in the previous one. And so I claim that each step we add one element, which is the ith root of the nth root of an element from the previous field. And so this makes it a radical extension. Okay. And this is, in some sense, we have already done the main part of the work. So by previous theorem, it is enough to show that the Gottsche group of Li of psi over Li, what was it? Yeah, minus 1 psi is cyclic of order Ni dividing n. Why is that? So I claim if we have shown, so Why is that? Because we know that Li minus 1 contains the primitive nth root of unity. So contains therefore also a primitive nth root of unity. For instance, I take this theta to the n divided by ni. And so we have an nth root of unity, and we have a cyclic Galois group of order ni. We know that if the ground field contains a primitive nth root of whatever, let's say nth root of unity, and the Galois group is cyclic of order n, then the field extension is given by adding the nth root of some element from the smaller field. No? Thus, by the theorem, we have that Li psi is equal to Li minus 1 of psi, comma, alpha I with an ni in element in Li minus 1 of psi. And so that means we have, so if this is true at each step, then this means this was a radical extension. Okay, so we only have to show that this Galois group here is cyclic for all I. So it's also, this is also obviously, okay, I mean, we know anyway that this extension is a radical extension, no? Because we have just added in nth root of unity, so there's no problem with that, so it's enough to do for the other ones. So we know that I said it, that Li over Li minus 1 is Galois. So this also means, so we can say, therefore, that Li is a splitting field of some polynomial, say G, in Li minus 1 of x. So thus, over Li minus 1. Thus we already know, so if we had this thing that we had used this trick before, so I first write it down, thus we have that Li psi, or theta, is the splitting field of x to the n minus 1 times g over Li minus 1. There was always the statement, so if we have a, this Li of xi is the splitting field of x to the n minus 1 over Li. No, obviously, because once you have a primitive root, it splits and it is a root. But we had this thing, if you have something which is, but this is already, this element already exists also, this polynomial already exists in Li minus 1, actually it already is polynomial with coefficients in k. So we have that if we have a, if we look at the splitting field, so what was it? If we look at so if you have a field expansion, so we had this thing, so if Li over So if L is a splitting field of some f in, say, fx over k over f, and f is a splitting field of say g in kx over okay, let me try again. Yeah, say x over k, and we have fx, and we have, however, this polynomial lies in the original ground field, this polynomial, then it follows that L is a splitting field of f times j, f times g over k. We've already used this a couple of times. No? So if we have we take the split, we have some field extension, so we have L over f over k are field extensions. With L is the splitting field of some polynomial over f, but the polynomial has coefficients in k. And f itself is a splitting field of some other polynomial in kx over k. Then, if I just take the product of those, the splitting field of that, then it will be this splitting field. This follows almost directly from the definition because we certainly have all the roots of f and g in it, and there's no intermediate field over which both of them will split. So, given this, so therefore, this is also a splitting field, so thus it follows. Thus it follows that Li of xi over Li minus 1 is Galois. Okay, so we want to use that. Now, we actually are basically done. So, as also Li over Li minus 1 is Galois, we see that so we have the same, such an, if you have an intermediate field which is Galois, then the Galois group of the bigger field over the smallest field will map the intermediate field to itself. This was one of the characterizations of being Galois or normal. So thus the elements of the Galois group of Li over Li minus 1 map Li to Li. So there are also elements in the Galois group of Li. So therefore we can make a restriction. So we have a homomorphism. Psi from the Galois group is just restriction of Li of xi over Li minus 1 of xi to the Galois group of Li over Li minus 1, which just does the following. It takes the homomorphism and it sends it to phi restricted to Li. By what I just said, an element in this Galois group, so this group is a subgroup of that, so that's okay. An element in this Galois group, here I wrote it with Li minus 1 without the psi, but this just means it's the element in this group which are the identity, on this on this intermediate field. So we have here this maps Li to itself. So if I restrict this, this is an element in the Galois group of L. Actually, will be an element in the Galois group of Li minus 1. So this thing is obviously an element in the Galois group of Li. Well, so this will be an element in the Galois group of Li, which is the identity. So this thing was the identity on Li minus 1 of Xi. So this is certainly the identity on Li. Did I want this actually? Yeah. So, okay. So this is an element here. And I want to claim this is injective. So see, I just take an element in the Galois group, I restrict it to Li. And this is a homomorphism, obviously, because if you restrict, because it's the composition, the group law. And so this is injective, so assume that phi is in the kernel of psi. So what does this mean? Then phi restricted to Li is equal to the identity of Li. But this was an element in this Galois group here. So that means phi of Xi is also equal to Xi. It's the identity of Li minus 1 of Xi. And phi of Xi is equal to Xi. So I have something which is the identity on Li and also the identity on Xi, so it's the identity on Li of Xi. Follows phi is equal to the identity on Li of Xi. So thus we have a surjective group homomorphism. We have an injective group homomorphism from this group to this group. This group is cyclic of order dividing Ni, so any subgroup will also be cyclic of order dividing Ni. So as the Galois group of Li minus 1 is cyclic of order dividing well, actually, in this case of order Ni, no? I think we get that the subgroup group of Li of Xi over Li minus 1 of Xi is cyclic of order dividing Ni. Okay, that's what we need to prove. Then this argument applies. So this, and and then to make this constructive, for instance, for the degree C thing, you have to remember how we constructed, how we found this alpha I with the Lagrangian resolvent, and so you can use this to make an explicit, get an explicit formula, for instance, for degree C polynomials. Okay, so much for this theorem. Are there questions? So you see, it's these are these things are somewhat complicated. I mean, it's also not like Galois invented this completely. People have worked on this for a long time. There, hope my that's interesting, but I can't see. So, yeah, and so this really is somewhat. It's not so totally easy, but now also everything fits together quite precisely, and you can see that this Galois theory is quite powerful, but it doesn't mean it directly solves almost any problem for you. It just allows you to translate it into something else that use some other tools, some tools from group theory or whatever to solve it. No, it's not a magic wand. Okay, so now, as we can ask ourselves, so, for instance, with all the story, can we give some explicit examples where some polynomials are not solvable by radicals? And that's actually quite easy. So you can, because here the criterion that we have been given, that the Galois group is not solvable, is maybe not such a great criterion. Because one of the things is that if you see a polynomial, it's not like you can normally immediately see, Galois group, obviously it's this one. It requires some thought. And so, so we want to see some way of having to see many examples where the Galois group is the whole symmetric group. So we know, I can prove it, that Sn, so symmetric group in n letters, is not solvable for n bigger or equal to 5. It's actually solvable for n smaller or equal to 4. So we give a criterion sufficient criterion for a polynomial of degree p, so p is a prime, so p is a prime, to have Galois group. SP, the whole symmetric group, and we give some kind of, you could, in some sense, you could see a geometric criterion. You can kind of check it by doing, high school calculus. Okay. It's really, and this is the following. Theorem over here. So let P be a prime number. No, that's so much. And I take F, so I just do it over the rational numbers, into X, be an irreducible. And we assume one more thing, so obviously of degree P. Assume F has precisely P minus 2 real roots. Okay? So for instance, if you have a polynomial of degree 3, then it should have one real root. Degree 5, it should have precisely 3 zeros over the real numbers, and so on. So then, the Galois group of F, by which I mean the Galois group of F over Q, is isomorphic to SP. Okay, so it's a very simple criterion, very geometric. If you write down, if you just make the graph of this polynomial over the real numbers, you can see whether or not it's solvable or not. I mean, at least not whether or not, but you can see that it's not solvable. It's not if and only if, just one dimension. So we somehow, so what's the point? You somehow have to find some elements in the Galois group. Actually, we'll have to find two elements in this Galois group which generate the whole symmetric group. And just from this fact.
Only two elements?
Well, we'll see.
But I think we cannot generate the group SP just with P minus 1 element.
Yes, we can. We can generate it by two elements. By some, not generate. It's not. We will see. I show you. Okay. because yeah. So let sigma equal to A1 to AP. P, so P is the set of roots of F, say in the complex numbers. And we say P minus 2 of them are real, so with the first group complex, the others real, so with A3 until AP real. So we take that L, so the splitting field, now I take it as a subfield of C, the splitting field of F. Q. No, anyway, it's a splitting field. So then we know that the Galois group of F is equal to the Galois group of L over Q. And we also know that this Galois group of F is isomorphic to a subgroup of the symmetric group on these roots, of all permutations of the roots that we have. No, if we have a Galois extension, if we have such a splitting field like this, then the Galois group is a subgroup of this, and so which is isomorphic. So this thing is isomorphic to SP, and which acting transitively on the roots. No, because the statement was that under these assumptions, the Galois group acts transitively. So if the polynomial is irreducible, then the Galois group acts transitively. This was under the assumption, so this was one of the theorems we proved. This was under the assumption that this polynomial has no multiple roots in the splitting field, but as we are in characteristic 0 and this polynomial is irreducible, we cannot have multiple roots in the splitting field, so that's fine. So this acts transitively, and now this is all we know. So from this, there's one more thing we know, and that we will now use. We obviously know that some of the roots are real and some of them are complex. So as our F is irreducible, we have that say if we add the first root to Q, this is degree P. So it's the minimal polynomial of any of its roots. So thus, if I take the order of the Galois group of F, this is equal to the degree of L over Q, as L over Q is the Galois extension and is the Galois group of L Q, which is equal to the degree of L over Q A1 times the degree L over Q A1 over Q. So thus P divides the order of the Galois group of F. Okay. So now we can use Gottshe's theorem. So if we have a prime number which divides the order of a group, then there exists an element of that order in the group. So by Gottshe's theorem, there exists an element sigma in the general group of F of order P, precisely P. Now, we have to ask ourselves, what can this element be? So, the claim is, so the only element of order P in the symmetric group, so I mean Galois F is a subgroup of SP, so the only elements of order P and SP are the P cycles. I mean that's could be an exercise or something. It's just if you have a cycle decomposition, then the order of an element is the smallest common multiple of the length of the cycles to which it is composed. So thus it means that sigma, that this is a P cycle. Okay, so we somehow maybe we identify, just to make sure, we identify Galois of F with a subgroup of SP by just using the numbering, no? So the permutation A1 permutated with A2 is the two cycle 1, 2, and so on. So this contains, so therefore, so thus rho is a P cycle. And so now let's see. So thus, obviously, this group will, if it contains rho, it contains all its powers. So thus, F contains powers rho to the k. And so obviously, if I take any power, if I take all powers of k, they will send a, so rho will send, so I don't know precisely what the rho does. Rho will send a1 to some other element, don't know to which one. But if I keep iterating, it will send it to any of these elements. So if I take rho, so because it's the, all the cyclic permutations, so the subgroups generated by rho is all cyclic permutations. And so I can send the first one to any element that I want. So by replacing, rho by power, we can assume that rho of A1 is equal to A2. No? We can just, it's if I go around often enough, I will can send it to anyone, so that I can choose this. And then the other ones here, so I have here, these A1 and A2 were the two complex ones, A3 to AP are elements in R. But here, the number, so the first two ones are special because they are different from the others, but these are just some elements in R. I can number them any way I want. So in particular, I can choose the numbering in such a way that row of A2 is equal to A3, row of A3, and so on, because it's just the, the choice of our column. So by renaming A3 to AT, we can assume that row of AI is equal to AI plus 1 for I smaller than P and A1 for I equal to P. No? So it's just cyclic like this. So thus row is just the cycle 1, 2, 3. P. Okay? So I have obtained, after possibly renaming these elements here, reordering these elements, only giving 1 and 2 as the first two, that we find this element as an element in the Galois group. Now, so that's one element. And there's one more element which we have in the Galois group. This I mentioned sometime before. Namely, complex conjugation is always an element in the Galois group. And we know that complex conjugation will fix, obviously, all the elements in R, and it will kind of interchange the two complex roots. So for complex conjugation, which is this complex conjugation is just interesting. A plus IB is sent to A minus IB. So this was called tau. This will always be an element in the Galois group of L over K. And we have that tau of A1 is equal to A2, because these are, two complex roots have to be complex conjugated. And tau of AI is equal to AI for I bigger than 2. So thus tau in this notation is just the transposition 1, 2. Is also an element in the Galois group. And now I claim that rho and tau generate the whole of the Galois group, the whole of the symmetric group. Okay, it's true that you cannot, that you need n-1 transpositions to generate Sn, but this element, together with one transposition, generates the whole group. And now, how does it work? Because basically by conjugation with this, you can get all transpositions. Let's look at it. So that's enough to show that 1, 2 and 1, 2 P generate SP. And that's nothing to do with it being a prime number. This would work always. The prime number we only needed to use Gottshe's theorem. If the degree was a prime number. Okay, and this is now actually quite an easy exercise. We just have to find all the elements we need. So we take, say, J between 2 and P. Then we can take rho, so the J minus 1, tau rho, so the 1 minus j. So we take the conjugation with this. And we apply this to some AI, where we want to have that, well, let's first do it. Now let me see. So where now I is different from j and j plus 1. Then let me just compute it. First I apply this. This is rho to the j minus 1 tau of a I plus 1 minus j. Maybe one has to, maybe do it cyclically or something. But anyway, maybe you can. So now, if this is different from this, then it follows that I plus 1 minus j is different from 1 and 2. And so if I apply tau to it, it acts as the identity. This is rho to the j minus 1 a I plus 1 minus j. And this is, the same. This is again AI. So to such an element it doesn't do anything. But if now if I apply to a j, so we do the same thing. This will be rho to the j minus 1 tau a1. Tau a1 is a2. This is rho to the j minus 1 of a2. This is a to the j plus 1. And in the same way, a j plus 1, if we do the computation, we get this is aj. So thus, we get that rho to the j minus 1 tau rho. So in this case, tau was there. Okay, tau rho to the 1 minus j. This is equal to j plus 1. So we get, if we have this one transposition and this rho, we get all transpositions between one and the next, and we know that these generate SP. You can express these generate SP. Okay, this is the proof. So you see, and so we have, and so thus we have figure out for that is actually equal to SP. So we can, you see, it's kind of, and obviously this is quite simple to check, because now it's some kind of, what do you call it? So the thing one does in school when you discuss functions, I don't know how it's said, you look at the graph of the functions, you want to know where the maxima, the minima, the zeros and so on. And so we can do an example. So look, for instance, I hope I get it right, f is equal to 2x to the 5 minus 10x plus 5. Okay. So we can apply the Eisenstein theorem with the for the prime 5. So this is irreducible by Eisenstein for the prime over 5. So it's therefore it's irreducible over Q. Okay. So now one can check the following. So f has a minimum at x equal to 1. And so how does one do this? Now you compute the derivative and you find there's a 0 at x equal to 1, and the second derivative has the correct sign, so that it's a minimum. Okay? So really like you learn in school. And you compute by putting it if f of 1 is equal to, I hope I got it right, minus 3, which is obviously negative. So we also find that f has a maximum at x equal to minus 1. Again, the same thing, no? The derivative is 0 and whatever the second derivative is negative. And f, hope I got it right, that it's 1 because I have shown, anyway, I hope it's right, otherwise the numbers are, and this will actually be 3. I have chosen it apparently quite symmetric, and there are no other extremal values.
It is 13.
What?
F of minus 1 is 13.
What?
It's 13.
13.
F of minus 1.
Ah, okay. Yeah, the question is whether this is right. I mean, I don't have the computations with me, so I don't quite know. It could also be minus 3, so let's just see. If we take the derivative, what is it? This is 10x to the 4 minus 10, so that's not very difficult, so I can have x to the 4 minus 1, so we have 1 minus 1, yeah, so it's minus 1, and you say it's 13. Well, if you say so, that expect it's right, okay, so I hope it's 13. Anyway, it's plot, it's bigger than 0, not everyone. There could be a misprint here. And so, and obviously, if for x going to infinity, you know, as the leading coefficient is positive, it goes to infinity. And for x going to minus infinity, f of x goes to minus infinity. Okay, so this is here. And so we can make just the qualitative drawing. So we have, so somehow here, the real line. So, so maybe it's 0. Here is 1, here's minus 1. So at minus 1, it has a maximum. No, at minus 1, so at minus 1 it has a maximum. Is this right? Yeah. And you have, and the value is positive. So we have somehow this. Then at 1, it has a minimum and it's negative. And there are no other extremal values. So if it somehow would go here and come back, it would have to have another minimum. So the only way is it can have only 1 0 in this. So you can have precisely 1 0 in this interval. No, in this interval there's precisely 1 0, because here it's positive, here it's negative, so there must be a 0. And if there was more than 1 0, it would have to have another minimum or maximum, because it has to go down and come back. There's only 1 0. And then it goes to infinity here. It has no other extremal values, so it has to cross the line somewhere, and it cannot cross it more than once, because otherwise you would have to have an extremal value and the same. And so you have 1 0 in this interval, precisely 1 0 in this interval, and 1 0 in this interval, so you have 3 zeros. And so it follows that this polynomial is not solvable already. So you don't have to do something totally crazy. It's actually quite okay. So that was that. I mean, you can make many such examples. So now I wanted to talk a bit more about roots of unity, rather about the extension you get by roots of unity, what the corresponding Algebra group is, and so on. This also has some, I mean, if you want a little bit of number theory in it, not very much. And if we have enough time, we see a geometric application of it in the last lecture. So this is, I want to talk more about roots of unity. So basically you want to know, if you take Q and add to it a primitive root of unity, what's the Algebra group? And what's the degree of the field extension, and so on. So we work over the ground field K, which is just Q. So let L be an extension of Q. And theta in a primitive n of unity. So if you wish, you can take e to the 2 pi I divided by n in the complex numbers, but it works also in a more abstract setting. So primitive n root of unity, as you know, means that its nth power is 1, and if it has a smaller power, then smaller positive power than n is not 1. So we want to describe this Q theta and the Algebra group of Q theta over Q. So first, this has something to do with the number theoretical function, which is the Euler phi function. So I will write Zn just as a shorthand for Z modulo Nz. Anyway, I have defined this slightly differently by isomorphic, but now I just write this to save some confusion. So let Zn star be the group of units in Zn. Okay, this is, so we have Zn is a ring, no, with additional multiplication, and we can look at the units, so the invertible elements. So that's one thing, and we can also define something else, which is cannot be rated. I can map from the positive integers to the positive integers, which sends an integer to phi of n, which is, so it's the number of elements in the following sets. It's all the integers which lie between 0 and n and are relatively prime to n. So the greatest common divisor of k and n is 1. They don't have common divisors. Okay, this is called the Euler phi function. So phi is called the Euler phi function. So And I mean, I expect you will see it also in Tatiana's in the seminar on, or maybe you have already seen it. So we want to describe it a little bit and relate it, so proposition. Want to relate it to these units here. So for all positive integers, we have that if I take the units in the n, this can be described as the set of all equivalence classes k in z mod nz, or as I call it zn, such that the greatest common divisor of k and n is equal to 1. They are relatively prime. So this is 1. 2 is that for every n, in z bigger than 0, the number of elements, the number of units in Zn is this number phi of n. And note this follows directly from 1, because the elements here are just these are the equivalence classes of elements k from 0, which are, the elements here are the equivalence classes k of a number k between 0 and n, and we require it to be relatively prime to n, which is precisely how I have defined phi n. So obviously 2 forward 1 implies 2. Then the third one is, this is what is sometimes in number theory called a multiplicative function, namely if the greatest common divisor of n and m is equal to 1, so if they are relatively prime, then it follows that if I take phi of the product, this is phi of n times phi of n. Okay. And the fourth one will turn out to be a consequence of the third again, but I can review it later. So if n is some positive integer, maybe actually bigger than 1, with where I can write n as a product of prime power, so p1 to the l1 times pr to the lr for distinct prime numbers. P1 to PR, then it follows that phi of n can be written as a product from I equals 1 to R of P to the Li minus P to the Li minus 1. Yeah. Okay. So this is more or less what one can know about this function.
What's the P?
Pi. We have these prime numbers P1 to PR, and then. Okay. This is actually quite simple. I mean, here one just looks at the first one is very simple. Just look at the definition. So if K is an element in Z, not NZ, then K is a unit if and only if it has an inverse. With K times P prime is equal to 1. But this just means that I can take a number, I can write, I can take a number so I can choose K to be a number from 0 to n, and k prime is a number from 0 to n, and then this product must be congruent to 1 mod n. So that means there exists a k prime in 0 n minus 1 with k times k prime is equal to a n plus 1 for a some integer, and this is equivalent to saying that k and k prime, k and n are relatively prime. Okay, so that means therefore that the first statement here holds, and the second we have, and now we come to this one. That's slightly more effort, but it's quite straightforward, we know. So we want to show, so this is 3, want to show that if I take the units, so we have n and m are relatively prime. So we assume that n and m are relatively prime. We want the units in z and m. We want to show that in a suitable sense this is isomorphic to the units in Zn times the units in Zn. No, as a group with multiplication, they are isomorphic. So how does it go? So the map, we have so we first have to relate z and m with zn times cm. So the map z and m to zn times cm, which sends some number k plus nm times z to k plus nz, k plus nz. I want to claim that this is an isomorphism. So first, it's clearly well defined, because if k plus, if it sends equivalence class to equivalence class, because this class is smaller. So if this is a group is a ring homomorphism. Well, so that, yeah. But at least it is it certainly so it is a ring homomorphism where multiplication here is component-wise. You can check that. And what is its kernel? If I take k plus mz is equal to 0, and this is also k plus nz is also equal to 0, which is equivalent to saying that k is an element in mz and k is an element in mz, in nz, so that is m divides k and n divides k. As they are relatively prime, this is equivalent to nm divides k. So therefore we see that this map is also injective. So the kernel of this map is 0, so nm. So that's the homomorphism is injective. So I have an injective ring homomorphism from this to this, and obviously both of these have n times m elements, so therefore it's an isomorphism. So as both have n m elements, it is an isomorphism. So, in particular, it follows, so thus, we have that if I look at the units in Nm, this is equal to the units, isomorphic to the units at M. Okay? And so we only have to see that the units like this are like this units, and that's almost by definition. Because, you can see phi and m is the number of elements of this. Okay. So we have to show that this is the case. And then it's clear the number of elements. This phi n is the number of these elements, and this is equal to the number of these elements times the number of these elements, which is phi n and phi n. Okay, and this is basically by definition. So as AB is a unit in Vn times Cm, if and only if there exist elements A prime, B prime in Vn times Cm, such that A prime, B prime is equal to 1, 1. And obviously that's the same as saying that, so this is equivalent to saying that there exists A prime, B prime, so in Cn, B prime in Vn, such that A prime is equal to 1, B prime is equal to 1. And that's it. Okay, so that's quite simple. And so this proves part 3. Now we finally come to this. So maybe I can write it here so that so now if P is a prime number, we want to see how many elements it has then, and say L is bigger than 0, then in the numbers from say 1 to PL, which is the same as the numbers from 0 to PL minus 1, which are not prime to P to the L. Well, this will be to be not prime to P to the L means to be divisible by P. So R precisely P times M, with M any number, so P to the L minus 1. From 1 to P to the L minus 1. So that means that the numbers which are relatively prime, the numbers from 1 to P to the L which are relatively prime to P are P to the L minus these, and these are P to the L minus 1. So thus phi of P to the L is equal to P to the L minus P to the L minus 1. And now we can just put it together. So if we look at this formula here, if I take phi of P1 to the L1 times P R to the LR, so the Pi to the Li are all relatively prime to each other. So I can write this, say, as phi of P1 to the L1 times phi of P2 to the L2 times P times P R to the LR. So this I know by induction, and this one, so anyway, this will be P1 to the L1 minus P 1 to the L1 minus 1, and this is computed by induction. So P2 to the L2 minus P2 to the L2 minus 1, and so PR to the LR minus PR to the LR. Okay, so this is this proof. Let me see whether this is. Yeah, don't think I can do the next remark. So maybe I will stop here. So next I will. So then in the next I will apply this to these roots of unity. So somehow we will see that this phi function has some. I mean, one of the things we will actually, for instance, prove that if we take the degree, actually we'll not quite prove it, but more or less, if I take the degree of Q of theta over Q, the degree of this field extension, where theta is a primitive entity of unity, this will be equal to phi of x. Okay, so that, and if you have time, I can in the end use this to sketch the proof of Gauss, which regular polygons can be constructed with ruler and compass and which can't. There's a kind of very non-trivial, somewhat non-trivial result, a kind of a strange criterion. So for which n can you, with ruler and compass, make a regular n norm by the Greek method of constructing it? This was something that Gauss, I think, he did this for the regular 17 gon or something when he was maybe 18 or 17 or something. And this was very important for mathematics because he had put himself this task to decide whether he wanted to become a mathematician or a linguist. And so he solved this, and so he became a mathematician. And so otherwise there would not be. Okay, and so therefore, yeah, no, it was.